Hello and welcome to Empowered Learning. This video will be about solving first order separable ordinary differential equations. So in this video, what we're going to do is review what a first order separable differential equation actually is. We're going to quickly go through the steps that we need to consider when solving these types of equations, and then do several examples of solving these types of equations. So a first order ordinary differential equation is called separable if we have the situation where we have dy over dx. Well, y is just assumed to be some function of x here, where the function on the right hand side is both a function of x and or y. Okay, and specifically we say that we can rewrite this function of x and y as f of x multiplied by g of y. So that means we have a way of being able to rewrite this particular expression here to where we end up with a function of x times a function of y. So if we're able to do that, then we have a separable ordinary differential equation. Now, the reason why it's separable is because if I'm actually able to rewrite this ordinary differential equation in this way, I can get all terms with x on one side and all terms with y on the other. And of course, if I rearrange this particular equation to do that, I would have something that looks like this, where this h of y here is actually just the reciprocal of g of y. Okay. So the steps for solving separable equations are as follows. And so I'm going to quickly go through this because I don't expect you to remember all this verbatim, but I just want to use this as a frame of reference so that whenever we solve these ordinary differential equations in the examples I'm going to do, we're going to refer back to this list. Okay. So the first thing that we want to do is get the ordinary differential equation in this form, okay, so that we know that it's separable. The next thing that we want to do is, once we have it in this form, we could look at what the g of y is and figure out if we're going to have any constant solutions or not. Because if we have a constant value that we can plug in for y here that will make g of y go to 0, then it would make this entire derivative here go to 0, and thus it would be a constant solution. Okay, so first we want to get it into this form so that we can recognize whether we have any constant solutions or not. From that point, step 3 is to basically get this rewritten into a form that looks like this. Okay, and so you're going to see in the examples that I do, at least for some of them, I'm going to take a more formal approach to actually getting it into that form. There is a quick and dirty way to do it, and I'm going to resort to doing that for at least half of the time, but I am going to do at least 1 or 2 examples where I show you the formal way of doing it, only because it's really an issue to try to break this up, meaning that dy over dx actually just means y prime of x, and in this notation here, we really shouldn't break up the dy and the dx from each other. But technically, I mean, we could still do it. So I'm just going to show you what it looks like if we, stay formal and rigid. And of course, in practice, you can just break it up and do what you need to do to solve these types of equations here. So for step 4, we want to integrate both sides of this particular equation here, and notice that I just have this as y prime, which is the dy over dx thing here, and we're noting here that y prime of x is dy over dx, which we know from first year calculus we could rewrite this in terms of a differential in terms of y. Okay. And so this is like the more formal way of doing it. And because of this, we could take this particular equation here and we could multiply both sides by dx. And of course, by definition, that's y prime of x times dx is just going to give me dy. And that's how I formally get it into that form. About 2 or 3 extra steps that you would have to do to keep it in formal fashion. But again, it's depending upon what course you're taking and how picky your professor is on actually, writing that out or not, you may or may not need to do it. Now, please note that in step 4, we're getting it to this point so that we can integrate both sides. And when we do this, if you have an initial value problem, you do have the option of using definite integrals to be able to do it. If you don't want to do that, you can just use indefinite integrals. And then once you actually get what your actual solution to the differential equation is going to be, you can go ahead and sub in your initial conditions afterwards. In the list of examples that I'm going to do, I'm going to do the last example using these, the definite integral technique for. I personally like to do the indefinite integral first and then come back and do the initial conditions later, just because for me, it's a little bit easier to do. I have things kind of broken up, but you can do it this way if you want to keep everything compact and together. And I'll do at least one example so you can see what that looks like. All right, so step 5, once we have it in this form and provided that h of y and f of x are functions to where they have elementary function antiderivatives, we will go ahead and try to solve for y, okay? And that will be the function that's supposed to be the solution to the differential equation. Now, we try to solve for y explicitly in terms of x if we can. If not, then we just try to leave it in the best, cleanest way possible, okay? Now, the last step, and this step sometimes, depending upon, again, how particular your professor is, you may or may not have to do. I know personally for the courses that I teach, I pay attention to this sort of thing because it's important for you to be able to actually use your results from solving differential equations in application. So I think it's something that's important to consider. And so that is, we want to see if the constant solutions that we have, if they can actually be combined with the non-constant solutions that we have, okay? Now, the reason that we want to do this is we want to find the most compact way of being able to express our answer. And so you're going to see examples to where we will have solutions that are all constant, well, only constant, I should say. We'll have solutions that are only non-constant, and then we'll see some solutions that are both constant and non-constant. And sometimes we may not be able to wrap the constant solutions in the non-constant solution. Other times we can see for a particular value of x, we'll get the constant solution or solutions. And so we can just kind of say that, hey, the non-constant solution is the actual solution to our differential equation. And note that, hey, if x is 1 or if x is 3, then we get that specific constant solution type case. All right, so for our first example here, we just want to review to be able to look at a first order differential equation and know whether the equation that we're looking at is separable or not, okay? So in the first 2 examples that I have here, you see that this first equation here is one that's not separable because in this form, there's no way for me to rewrite 3x minus y times sine of x as a function of x times a function of y. Okay, no way to do it. However, in the second example, we see that if I use factor by grouping, I can rewrite this expression on the left to be written as a function of x times a function of y. And thus, because of that, this particular differential equation is separable. Okay. Now for this example, again, there's no way for me to actually rewrite sine of x plus y to make it end up being a function of x times a function of y. No way for me to do that. Even if I use the addition formula for sine, still is not going to be a function of x times a function of y. So in this case, this is not going to be separable. Now, in this case, I could rewrite this as e raised to the x times e raised to the negative 3y squared. And thus we have a function of x times another function of y. So because of that, we know that this is actually a separable first order differential equation. All right, so for our first example here, and this will be the instructions for most of the examples that we do, we want to find a general solution, including any constant solutions, if possible, for this differential equation. We also want to write our final answer as an explicit solution where possible, and meaning an explicit solution of x possible. Okay. Now, for this first example here, you see I've already worked it out, and part of the reason I've done that is to show you the formal way that we solve these. I'm actually going to do it the informal way too, so that you see the difference. So the first thing that we would like to do is rewrite this particular equation as, in this case, dx over dy will be equal to, some function. And so here, to do that, first thing I do is I rewrite y plus 1 divided by x quantity squared. It's just y plus 1 squared divided by x squared. And then from there, I go ahead and multiply both sides here by x squared. Okay. So x squared, and also divide both sides by y. So that's how I get the y down here. Once I do that, then for here, notice that my dx over dy, so I know that x in this case is assumed to be a function of y. And of course, the derivative of x in terms of y, of course, we could think of that as dx over dy in Leibniz notation, okay? So if we look at it this way, of course, we know from first year calculus that if we wanted to rewrite dx in differential form, it would look like this, okay? And technically, really all we're doing is taking this and multiplying dy to both sides. So if you want to look at it from a practical sense, that's what's actually going on when you try to summarize it. But there's a whole lot going on in this statement here that says that, no, that's actually not it. But once you kind of go through all the hoops and whatnot, it still ends up being that's what it is. Okay. But again, I know some textbooks, they are very particular about this and say, no, you write it this way. So I wanted to make sure that if you're in one of those courses, that you know how your work should look. So for here, we can just replace the x prime of y with, well, we can't replace it yet, but we're going to multiply both sides by dy first so that we can get it into this form so that we can replace that with just dx. And so at this point, what we end up having is a side where you have everything in terms of x, and this side over here with everything in terms of y. And of course, the reason why this looks this way is that we've expanded out the numerator, and then of course divided all terms on the right side here by y. Okay. Now, at this point, I note that to identify your constant solutions, one of the things that we could do is we could, I guess if we wanted to do this as dy over dx, if we wanted to look at it that way, we could solve this for dy over dx, okay? And so if we did that, then of course, we would end up rewriting our functions this way, okay? And so if we looked at that, we're trying to look at what constant value can I plug in for y in here so that it makes everything here go to 0, okay? Now, to be simple, short, and sweet, we're only considering this portion of the right-hand side of this equation. And of course, if we let y equal 0, then that makes g of y go to 0, which makes everything on that right-hand side go to 0. So we know that the only constant solution that we have is the trivial one, which is y is equal to 0, okay? Now, I also want you to note that if we were to look at this another way, and so I just did this as considering dy over dx because it's more of the traditional way of doing this. But what if we were looking for what is going to be the constant solution for this case, okay? Well, if we did that, then of course we would have to look here. And so the issue here is that the only value of x that might possibly make this expression go to 0 is 0. But if I plugged in 0 here, we know that natural log of 0 is an undefined number. So if we looked at it in these terms of saying, hey, let's let x be a function of y, then we would have no constant solutions in terms of x in this case, okay? So my point here is that it really kind of depends upon if you're trying to find out what dx over dy is, or if you're trying to find out what dy over dx is. In this particular example, I am trying to solve for what y is in terms of x, okay? Or put another way, I'm trying to get everything to where I eventually have it as dy over dx, okay? All right, so moving on here. So taking note that we have a constant solution of y equals 0, we go and try to see if we can find the non-constant solutions. So here I take basically the indefinite integral of both sides. I'm going to take the antiderivative, and I'm going to look here and here, and I say yes, for both sides I can find an antiderivative for the left and for the right, relatively easy. And of course, for the left-hand side, I would have to employ integration by parts to do that. For the right-hand side, I can just take the antiderivative of each of these three terms normally and separately, okay? So we'll work a bit on the integration by parts piece of this. So for integration by parts, I'm going to let the x squared be the u and the natural log, natural log of x dx be the dv. And I just take it through the whole thing of integration by parts. And I'm assuming that you already know how to do that. So essentially, this is just going to be uv minus integral of v du. We figure out what the derivative of u is, antiderivative of dv is, and then we just work it out. Now, note that here, how we actually figure out that the antiderivative of natural log of x is just x times natural log of x minus x. You can actually do integration by parts to do that as well. But this is one of those well-known things, so I just wrote it down and we're going to roll with it. So from here, we see that to try to find the antiderivative of the left side, which is the same as trying to take the antiderivative of u times dv, is formula here, uv minus integral of v du. Substitute everything in, and then the rest of what we're seeing here is just me working through all of that to get to final answer, okay? Now, as I start to work through this, one of the things that I notice is that, all right, I get to this particular portion here, and so then I clean everything up. and I say that, all right, well, the right-hand side, and I'm going to erase this here and write what I originally had, which was the indefinite integral of x squared times natural log of x dx. So what we have here is integral of x squared times natural log of x dx, and that is equal to all this business here, okay? So in this, notice that you have this term here that has integral of x squared times natural log of x dx, and we also have that here. So this is one of those situations where from our answer, we could rearrange terms so that we can actually solve for integral of x squared times natural log of x dx, and whatever else is left on the right-hand side once we're done, and we get that by itself is what the answer would be, okay? So that's why we have the situation here. Of course, if I added this particular term here to both sides, then I would end up having 3 times integral of x squared times natural log of x dx equal to everything else that's left on the right hand side. And then I divide all sides, both sides by 3, and then I end up getting this result here. And so that's what the left hand side of my original equation here that I was trying to solve for is, okay? Now, the right-hand side is relatively easy. We know that any derivative of y is just y squared over 2. Any derivative of 2 is just 2y. And any derivative of 1 over y would be natural log or absolute value of y. And so here we see that those are those 3 terms I just talked about. Here is our integration constant because of the fact that we did indefinite integrals. And we did not have any initial conditions, so we just leave this way. And so now what we end up doing here is saying our final answer is just going to be all of this. And what G ends up being is just going to be F. And of course, F is right here times D. And what D is, it came from here, which is just C divided by 3. Okay, so we're just combining constants there. And so with that, that ends up being our answer for this particular question. And notice here that we kept it in this form because to try to solve for y exclusively in terms of x, or as x exclusively in terms of y, it will be very painful to do, and it's really not worth the time to do it. So we just leave it in this form here, okay? All right, so let's move on to our next example. So for this example, notice that we could rewrite the right-hand side as e raised to the 3x times e raised to the 2y. So what this ends up being is a separable ODE. Now, that's important to us because now that we know that it's separable, we know what strategy we should take to be able to try to solve this differential equation. And also this gives us an idea on if we have any constant solutions or not, okay? Now, since we have dy over dx here, what we are looking for are functions of y so that if I plug in a particular constant in for y, I make the whole right-hand side of this differential equation go to 0. Now, this is going to be my function of y. However, I know that this particular function will never equal to 0 for any value of y within the real numbers. And I know that because it's exponential, okay? We know all exponentially increasing functions that do not have any kind of, I'll say, vertical shift up or vertical shift down, is going to touch or cross the x-axis. So because of that, we have no constant solutions. And we know that because there's no value of y I can plug in here to make everything go to 0. Okay. So now that we have determined that, we're going to look for non-constant solutions at this point. Okay. So here I'm going to say that dy over dx is equal to what we have here. And of course, if we look at this formally, we know that dy over dx is equal to y prime of x, which means that dy is equal to y prime of x dx. Okay. And so if we did this formally, we would just replace the dy over dx with y prime of x here. And one thing that I could do is divide both sides by e raised to the 3x to get this portion here on this side. If I did that, then I would just have e raised to the 2y on the right. And this could be e raised to the negative 3x times y prime of x equals to e raised to the 2y. And as a result, at this point, to do it formally, I could multiply both sides by this dx here so that I could end up having a dy on this side. So if I multiply this by dx here, that by dx there, let's see. Yeah, that's not looking the way that I wanted it to look. What happened? Oh, yeah, that's what happened. Yeah, let me back up here. Yep, so let's back up here. So hopefully you see by me working it this way, you could see how I kind of recognize that, hey, it's not in the form that I needed to be in. So when things start to look strange, you could kind of correct yourself. All right, so here let's do all right, so this is going to be y prime of x here. And this will be e raised to the 3x times here. And if we divide both sides by e raised to the 2y, and I'll have this situation here. This is what I should have done the first time. And then after that, the next step would be we have e raised to the negative 2y times y prime of x is equal to e raised to the 3x. And then from there, if I multiply both sides by dx, then I'll have e raised to the 2y times y prime dx equals to e raised to the 3x dx. And all of this is just a fancy way of saying dy. So what we end up with is this situation here. Now note, if we were to just do this the informal way, this would be a whole lot easier to do. And this is why most people do it. So if we were allowing ourselves to be able to break up this dy over dx here, then I could simply just rewrite this as dy over e raised to the 2y and e raised to the 3x times dx here. And I would essentially just have this situation here. And so in practice, this is how most people actually work these equations here. But technically speaking, because dy over dx is it's an operator for a derivative, and we really shouldn't break it up. That's why I'm doing it the other way in the problem that I was currently working on. So just to let you know that I'm going to do this formal way for maybe like one more example, and then after that, we're just going to do it this quick and dirty way from now on. Okay. All right. So from here, then all we really need to do is take the indefinite integral or antiderivative of both sides. Of course, this is going to follow the substitution rule. So when we do that, we're just going to have e raised to the negative 2y divided by 2 on the left-hand side, and we'll have e raised to the 3x divided by 3 on the right-hand side. And of course, both of these sides actually have integration constants, but I'm just going to write 1 here to represent both. Okay. And so now at this particular point, what we can do is just try to, we're going to try to solve this for y in terms of x explicitly. So what I'm going to do to try to make life a little bit easier is multiply both sides by a negative 6. So I'll do my negative here. And so if I do that, then that's going to give me 3e raised to the negative 2y here. And on the other side, it's going to give me 2e raised to the 3x minus 6c. Okay. And so from here, again, I'm just trying to get y by itself here. So the next thing I'll do is divide both sides by 3. And this will be e raised to the negative 2y. And on the right-hand side, this will be 2/3 e raised to 3x minus 2c. And then from this point, I can just take the natural log of both sides. And that would get that minus 2y by itself. So I have that. And of course, from here, what that would mean is on the left-hand side, I'll have minus 2y. Left-hand side, sorry, right-hand side would stay the same. And last thing I'll do is divide both sides by a negative 2. So this would end up, I feel like I'm forgetting something here. Yes, I am. Yep. So this should be a negative 6 right here. So here, this should be negative here, which means negative here, which means negative here, negative here, and negative there. All right. And so this is what our final answer would look like as y explicitly defined in terms of x. To make this look a little bit cleaner, I could replace this minus 2c here. I could just say that this is just this plus d. Of course, where d is equal to minus 2c. Really doesn't matter because at the end of the day, it's just going to be a constant anyway. Okay, so we like to express our answers in this particular form in the cleanest way possible, with the least amount of baggage when we start naming the integration constants as possible. And so this would be our answer. Notice that, again, we did not have any constant solutions for this one. So this is an example of where we only have constant solutions as our function that satisfies the ordinary differential equation. All right, so for our next example, this is one where we've already worked it out. But here we have secant squared x times dy plus cosecant y times dx equals 0. In this case, you see that I'm trying to rearrange this particular equation here so that I can eventually have dy over dx is equal to something, okay, if I can. So in this case, notice that when I do the rearranging here to get it to this point, notice that I have minus secant of y in the denominator and secant squared of x. And I know that these two expressions here are not going to be able to equal to 0. Okay. Now for secant of y, I have here that y should not be equal to 0. In reality, it should be y is not equal to n pi, where n is some integer. Okay. Because again, we know cosecant is just a reciprocal of sine. So if I had 1 over sine y, we know that sine of y is going to equal to 0 whenever y is either 0 or pi or 2 pi, 3 pi, 4 pi, just integer multiples of pi, okay, regardless of whether they're positive or negative. So we want to keep that in mind. With secant squared, again, that's the same as 1 over cosine squared, main function there being cosine. And we know that for odd integer multiples of pi over 2, cosine would be 0. So therefore, secant would be 0 for odd integer multiples of 2. So that's why I have this here. And again, I'm keeping track of this because this may pop up later on in us being able to identify what values of y and x in this case are actually valid for the solution to this particular equation. So once we work this out, of course, the reciprocal of cosecant is sine. The reciprocal of secant squared is cosine. So we have this differential equation here. Now, and I haven't done this here, but I'm going to go ahead and do it now. If I was to rewrite this as dy over dx, then what this would end up looking like is this would be cosine squared of x all over sine of y. Okay. And so here, notice that there are no values of y that would make this particular derivative of y with respect to x go to 0, because I only have a function in terms of x in the numerator. So because of that, I'm not going to have any constant solutions for this particular function. For this particular equation here. Okay. All right. So from here, I notice that I have cosine squared x here and minus sine y here. I've separated everything to where I have everything in terms of x on one side, everything in terms of y on the other. And naturally, I would want to integrate both sides at this point. The issue here is that with cosine squared, we don't have a direct way to be able to take the antiderivative of cosine squared. So what we end up doing is using some of our trig identities, and that's what this is for. In particular, what we want to do is use one of the many trig identities for cosine of 2x to be able to get it into a form to where we can actually, take the antiderivative of it. Okay. And so what we actually end up doing is using what's called the reduction formulas. So we find a way to rewrite cosine squared being cosine to something to power 2 to something cosine raised to the 1. Okay. And so I go through the whole derivation process here of how to do that. And so once we're here, we're just going to replace cosine squared with just 1/2 cosine of 2x plus 1. Okay. And so once we do that, then I can handle taking the antiderivative of cosine 2x and take the antiderivative of 1 without a problem. Okay. And so from there, we just go ahead and integrate both sides. Of course, the antiderivative of minus sine is going to be cosine. And of course, for this first term here, we could use substitution rule to be able to take the antiderivative of that, and that's how we get the 1/2 sine of 2x. The antiderivative of 1 is just x. And so then from this point, again, our goal, if we can, is to be able to solve for y in terms of x explicitly. Okay. So I clean all this up on the right-hand side, and then I do the arc cosine on both sides. And of course, that frees up this particular y. And of course, we have arc cosine, or cosine inverse, if you like to express it that way, of all this business here. Okay. And so now we know that we can express this particular answer here in one of three ways. So explicitly as y in terms of x, we could express it how I have it here. If you chose to, you could express it this way, or you could multiply both sides by 4 and express it that way. It really doesn't matter. We like to be able to express it in this way whenever possible, just because, hey, if we know what x is, we can figure out what y is. Okay. Now, the only other thing I want to say here is that we need to identify what are the valid values of y and x for this particular solution. So if you remember, one of the things that we said up here was that y could not be multiple integers of pi, and x could not be odd integer multiples of pi over 2. So that still holds. So when we come down here, we want to make sure that, of course, y is not going to be integer multiples of pi, and x is not going to be odd integer multiples of pi over 2. Now, the assumptions that we've made here would make a whole lot of sense if our result was actually a periodic function. But notice that this is arc cosine or cosine inverse of something. Of course, we got a lot of something in here, but we know whatever it is for arc cosine looks like this, where this would be pi over 2 here. That particular function looks something like this. So we know that this particular function is not going to be periodic. So even though what we had here in the beginning would hold, we see that there's only going to be specific values here for which this is going to be valid. Okay. And so in other words, there are going to be specific values of n for where this would work. And then for all others, we would have to exclude them. Of course, the problem here is that we have a constant here, and unless we have an initial condition, we're not going to know what that exact solution is going to be. And so the best that we could possibly do is try to rewrite this, what the actual x values we could have and thus corresponding y values would be, in terms of c. Now, to make life a little bit easier for us, what I'm going to do is I'm going to go to Desmos right quick, and we're going to see what this actually looks like whenever we plot the solution for several values of c, just so that we can get an idea of what it means to have an infinite number of solutions for a particular equation here. Okay, so I've taken our explicit solution here and I've put it into Desmos, and you see, and I'll just get it when c is equal to 0. this is what it would look like when c is equal to 0. So roughly, let's see, it's 1, 2, 3, 4, 5. So this is roughly about 2.5 right here. Roughly about negative 2.5 right here. So that would be the domain of x values. Of course, y values, if you notice, a little bit above 3, and of course 0 here. So that's looking like from 0 to pi, basically. Okay. Now, of course, if I slide this, you see how it, as the values of c get higher, the more the graph moves to the left. Okay. And I'll move this over so you can see what that looks like. The more this gets negative, the more it slides to the right here. Okay. And so depending upon what corresponding values of x and y we would have, that would let us know which one of these constants we would actually have here. And so that's the importance of having the initial conditions. Since we don't have the initial conditions, what we have is a bunch of these functions that are, sliding like this or going back like that. If you can just imagine having all those functions kind of stacked up on top of each other, that's what the actual solution would actually be here. Okay. And so I wanted to make sure that you saw that, because once you're actually done solving these equations, most of the time we're using it for something. And in this case, since it's like cosine inverse, then it's actually measuring some angle. And so we're saying that, hey, our solution here is an angle that goes in between such and such and such and such. Okay. And from what it looks like here, from what I can see, is going to be in between 0 and pi. And depending upon what your value c is, that will let me know what corresponding x and y values go with that. Okay, so for our next example here, we want to do the same thing. We want to figure out what y is in terms of x, if we can, but if not, at least get a solution to this particular equation. So if I rewrite this as dy over dx, and this will be y squared plus 1, all that over x squared plus 1. You'll notice here that in this form, we look at the numerator to figure out if we have any constant solutions. And of course, y squared plus 1, the only way y squared plus 1 is equal to 0 is whenever y squared is equal to negative 1, which means y would have to be a plus or minus I, which is a complex number. And we don't consider complex values for constant solutions here. So we will say that we do not have any real valued constant solutions for this particular differential equation. Okay, so we'll go ahead and get rid of this. And then we'll continue on with actually solving this differential equation. So with that being said, we are now in a situation where we want to get everything with x's on one side, everything with y's on the other. And of course, if we do some algebraic rearrangement here, basically we can switch the places of the dx here and the y squared plus 1 there. We would have dy over y squared plus 1, and this will be dx over x squared plus 1. And of course, from here, we can just integrate. And on both sides here, this should look very familiar to you. 1 over y squared plus 1, if we integrate that, the antiderivative for it would be arctan of y. And similarly, on the right side, the antiderivative of that would be arctan of x. So we'll have arctan of y equals arctan of x, and I'll just say plus some constant. Okay. And of course, at this point, if I wanted to write y in terms of x, I would just do the tangent to both sides here. And tangent of arctan would just be y. And of course, I'll have tangent of arctan here plus c. And so, of course, notice that this is our non-constant solution. And of course, in dealing with this, we have to consider, the values of y and the values of x that would actually be valid here. In this case, for arctan of y and for arctan of x, in general, arctan is a function that looks like this. So if we're talking about the independent variables, whether this is x or y, if we're looking at this as the x-axis, then it would be all real numbers. If we're looking at this as the y-axis, it would still be all real numbers. So we're good there. Okay, so for our next solution, we see that we have dy over dx is equal to this expression here. And notice that both terms has in common a y squared. So if we were to factor that out, we would have the situation here. And notice that from this, we're only looking at the y squared factor. This lets us know that y equals 0 would be a constant solution. And we know that because if I plug in 0 here for y, it makes all of this go to 0. Okay. Now, notice we do not pay attention to this factor here, meaning we don't pay attention to the function of x, because again, this is y is going to be a function of x, it's assumed to be. So this has no bearing. Okay. Even if we did, notice that sine here, the highest value it could be is a positive 1. Lowest value it could be is -1 for any value of x. So on the high end, we would have 3 minus 1, which would be a 2. And well, I say on the low end. And on the high end, this would be 3 minus a -1, which would be a 4. And so notice that what's in here, lowest it would be is 2, highest it would be is 4. There's no way this would go to 0 anyway. Okay. So even if we tried to work on it, it wouldn't work to give us any constant solutions. So this is the only constant solution that we have here. Okay. Now, now that we know that, we could deal with this equation as is, I guess in this form, and go ahead and try to solve for our function y in terms of x. So to do that, we can do some quick rearranging here. We'll divide both sides by y squared and multiply both sides by dx. And of course, from there, we can take the left side here and just rewrite it as y raised to the -2. So times dy, just to make it a little bit more simple to deal with. So this is y raised to the -2 dy. And then, of course, from here, we can integrate both sides. Okay. And so, of course, on the left side, if we integrate that, that's just going to be a -1 raised to the -1. On the right side, that will be 3x. And this would be a plus cosine because the antiderivative of minus sine is a positive cosine. And then we would have plus some constant. Now, of course, here we know that this y raised to the -1 is the same as 1 over y. So I'll go ahead and rewrite it that way. And so this lets us know that y is actually going to be a -1 divided by 3x plus cosine of x plus whatever constant this is. Okay. And so this would be our solution. And of course, just like how I said here, well, not here, but if we look at this, there's really not going to be any values of x here that's going to make all this go to 0. We wouldn't necessarily know that unless we knew exactly what c was. And since we're not really worried about that at this point, we won't dig too deep into all of that. But this would be the actual solution here. And so this is the non-constant solution. And so the point that I was trying to get at in mentioning the values of x or whatnot is, notice here that our numerator here is a -1. And there's no way that we're going to plug in anything for x to get 0 here. So if we were to express what the actual solutions to this differential equation would be, we would have to express it as y equals 0 and y equals -1 divided by 3x plus cosine of x plus c. Okay, we'd have to state them both explicitly because there's no way to wrap this solution into our non-constant solution. All right, so for our next example, this is an initial value problem, and we're going to solve it the same way. Only thing that's different is that once we actually get what our solution is going to be as either y in terms of x, or in this case, x in terms of t, we will go ahead and plug in our initial conditions to figure out what our integration constant would be. So we start off the problem the same. Since x is going to be a function of t, we look here and we see that this is an autonomous differential equation because our function here is x, and this is a function of that same function x. But notice that x squared plus 1, we're not going to be able to find any constant solutions that are real valued. So when we look at this, we know that we won't have any real value constant solutions because of that. So we look for our non-constant solutions. And again, here I go through the formal way of doing this, but essentially what I could do here is switch the place of dt and 4 times x squared plus 1. If I switch the places of those, then it'll eventually start to look like what you see here. Okay, and then of course we integrate both sides, and I'm doing the indefinite integral there. Of course, there's an understood 1/4 here that I factor out, and then the integral of dx over x squared plus 1 is just arctan or tan inverse, and the antiderivative of 1 dt is just going to be t plus some constant. And then from there, just multiply both sides of this equation here by 4, and I get this particular equation here. And then of course, I could take the tangent of both sides to figure out what x is in terms of t. And so this is what I would end up with here. And of course, in the whole thing of taking the, where's that? Yeah, so here, the 4, I could actually distribute that, and that's eventually where this 4c comes from later. Well, I'm not doing it here, actually, I'm doing it here. So let me just write it in. So if I write it in like that and I multiply both sides by 4, then that's where that ends up coming from. My point here is that this 4 here is sort of making that happen. So once we're there, then we just apply the initial conditions. And of course, since we know what x is explicitly in terms of t, all I have to do is plug in pi over 4 for t and let all that equal 1. And of course, when I do that, I end up just having tangent of pi plus d is equal to 1. And if you remember anything about tangent, we know that tangent of pi over 4 is equal to 1. So that is one of many values that it could be. But the reason why I only have pi over 4 here is because, remember, all of this actually came from a tangent inverse function here. So when we use this property of saying, hey, tangent inverse, and we're able to simplify here to x, there are certain assumptions that we are taking into, that we're taking into account. And of course, one of those assumptions here is that for a tangent, we are only considering the fundamental period of tangent here. So we're just considering this piece of it. And of course, pi over 4 would be somewhere around here, and this would map to a value of 1. So that's why we're only considering that specific value here for this result. And thus, because of that, d will just end up being a negative 3 pi over 4. And so all that I'm explaining here in this note is just basically saying that, hey, since we got tangent inverse and tangent, and we was able to get x or x of t by itself by this, then we have to assume that with tangent, we're only using this fundamental period for it. Okay? So because of that, we know that the only constant that we'll get for this will be negative 3 pi over 4. And so this supports the fact of whenever we have an initial value problem, like what we were talking about, if everything is well behaved and whatnot, and we have an initial value problem, then we know we have exactly one solution to that particular differential equation. And so here we see that the actual solution for it is just going to be tangent of 4t minus 3 pi over 4. And this is the only solution. And what that means is out of a family of solutions, and remember, a family is kind of like that example that I did with the arc cosine, to where depending upon what the constant is, the solution could kind of move up or down or left or right or whatever. But when we give a specific x and y value, then that means that when we give an exact constant here, that means there is a specific x and y value that goes with it, which pinpoints one particular function at one location out of the many functions that we have available to us. All right, so let's move on to this example. All right, so for this example, we want to do the same thing, find dy over dx. So we can start off by just adding a square root of 1 plus x squared dy to both sides. We end up with the situation here. And if we work this out, this will be square root of 1 minus y squared over square root of 1 minus x squared. And that will equal dy over dx. And so in this form, for your constant solutions, we consider the numerator here. We want to figure out when the numerator is going to be equal to 0. And that would imply that I figure out when the expression in the radicand is equal to 0, which in this case, we know that y is just going to be plus or minus 1. So these will be our constant solutions for this particular ODE. Now, with that out of the way, we're going to now look for our non-constant solutions. And so to do that, we're going to look back at this particular equation here, and we're going to get it into a form to where we can, take the antiderivative of both sides here. So to do this, what I'm going to essentially do here is I can basically take this square root of 1 minus y squared in dx, and I'm going to, by cross multiplying and some algebra, just rewrite it. And so this would be dx over 1 square root of 1 minus x squared. And this will be dy over square root of 1 minus y squared. And then, of course, from there, we can take indefinite integral of both sides. Now, if you remember here, 1 over square root of 1 minus x squared, if we took the antiderivative of that, that would be sine inverse or arc sine. And so since the left and the right look very similar, we know that this is just going to be arc sine of x on this side, and this will be arc sine of y on this side, plus some constant c. Okay. And so from here, and actually, yeah, I'll keep it that way. I know in the actual work I did for this problem, I actually made it minus, but I'll keep it plus for now. And so for here, what I'm going to do is I'm going to solve for y. And yeah, actually, I'll probably just need to do it that way because it's going to make life easier. It doesn't matter whether this is minus or plus, but I know that since I'm basically trying to get y by itself, I would like for this c over here to be positive. So that's why I'm just going to make it negative there. So from here, we'll have arc sine of x plus c if we add c to both sides. And this will just be arc sine of y. And then from there, of course, if I do the sine of both sides, then this would be sine of arc sine of x plus c, and that would just equal to y, which is basically y of x. And so this is what our general solution to our ODE would be in this case. And so this is general non-constant solution. And I'll write that. General non-constant solution. So now what we need to do is use our initial conditions here to figure out what this value of c will be. And so y of 0 equals square root of 3 over 2. That implies here that if I have sine of arc sine of 0 plus c, y of 0 here, if I do that, will just end up being square root of 3 over 2. And so this is essentially sine of c is equal to square root of 3 over 2, because arc sine of 0, that just ends up being 0. And so now in looking at this, one of the things that I hope you notice here is that this is well-known angle. And so the way I normally figure this out is I know sine is going to be opposite over hypotenuse for this right triangle. So that means this is a 1. And since square root of 3 is the second to largest side, that gives me the second to largest angle, which that would be 60 degrees. And since we're doing this in terms of radians, this would let me know that c is going to be pi over 3. Okay. And so because of that, my final answer would just end up being y of x is sine of arc sine of x plus pi over 3. And that would be my final answer for that. Now, one last thing that I want to talk about here is notice that for this particular problem here, this is non-constant particular solution. Okay. And notice that we have that along with this constant solution up here. Now, it turns out that the non-constant solutions that we have here could actually be worked into this non-constant solution here for specific values of x. Okay. And how we know that is remember that sine of pi is equal to 1. Okay. Also remember that sine of 3 pi over 2 is negative 1. And remember that arcsine of x is some angle. Okay. So here, if I was able to say, well, pi over 3 plus what angle would give me pi over 2, of course, this is the same as 60 degrees. So here, if I was able to find out what x value here would go along with this to where I had pi over 6, I could actually figure out the corresponding x value for that. Okay. And so it turns out here that we could actually figure out what those y values are. I'm sorry, what those x values are. And they turn out to end up being 1/2 and negative 1/2. Okay. And I want to show that right quick before we move on to the next example. So in order for get my pen here. In order for sine of all of this business here to equal 1, get some separation here. This will require that arcsine of x to be pi over 6. Okay. And so another way of saying that, if I did the sine of both sides here, I would say this is the same as saying sine of arcsine, which is just sine of arcsine of x, which is just x, is the same as just saying sine of pi over 6. And of course, pi over 6 is 30 degrees. I'll just write that here. And of course, sine in terms of 30 degrees would be opposite of the angle over hypotenuse. And that would be your 1/2. So that's how we get x is equal to positive 1/2. And so whenever we let x equal to a positive 1/2 here, that gives us our specific constant solution, y is equal to 1. Okay. If we did the same thing here and said sine of arcsine of this is equal to negative 1, so I'll just go ahead and switch this here. If it's equal to negative 1, then that would mean that arcsine of this, we could, I guess, make it real simple. We could say that is this. And of course, if we did the sine on both sides, you would have this situation here. And of course, since sine is an odd function, you can put the sign on the outside, and this would end up being a negative 1/2. Okay. And so we see that because of that, this answer here, we could express everything, constant and non-constant solutions, as just this one answer here. So if you're wondering, all right, well, what is the final answer to this differential equation in its most compact form? Well, this is it right here. Now, for this same example here, I did also want to share the fact that this answer could actually be expressed another way. And so this is actually another answer for this particular equation where x is bounded in between -1 and 1. And so what I do here is I just kind of show you, hey, well, why is this the case? And of course, from the example B on the previous page, we saw that our solution was this in explicit terms of x. And so if we just looked at the arcsine part, okay, and let's say we call it some angle alpha. If we let sine of alpha equal x by taking the sine of both sides here, then we know that x here would be limited in between -1 and 1, because that is what the domain of arc sine is, okay? And our angle here would be limited in between -π/2 and π/2. And of course, this is a graph of what sine inverse looks like. So basically, all I'm doing is stating what this graph already shows us. Now, if we use visual right triangle, like I used before, to do right angle trigonometry, we can express sine of alpha equals x in terms of a right triangle here. And what we essentially do here is we're changing something from being in trigonometric form to algebraic form, okay? And so we know that x is going to be opposite over hypotenuse. And of course, the side b, if we do what's better known as Pythagoras Theorem, even though it's not Pythagoras Theorem, we end up getting b is equal to square root of 1 minus x squared. And of course, if we were to rewrite this particular angle alpha now, in terms of what we have here, then if we use the addition formula for sine of a plus b, and of course, sine a cosine b plus cosine a sine b, we would see that we could rewrite this particular expression here, okay? And so when I rewrite it, of course, I have sine alpha cosine of π/3 plus cosine alpha sine of π/3, okay? Now we remember that sine of alpha is x, cosine of π/3 is 1/2. Cosine of alpha, if we look here, cosine of alpha, which is adjacent over hypotenuse, that is going to be square root of 1 minus x squared. And of course, sine of π/3, if we go back to the previous example here, sine of π/3 is square root of 3 over 2, okay? So if we take all that into consideration, then of course, and sub in everything, we see that this is an equivalent way to write our solution that we had back in example B when we did it, in terms of just x, okay, instead of in terms of x algebraically speaking, okay, instead of just having it with the trig functions in there, okay. And so finally, we note here that the graph of arc sine has endpoints at plus or minus 1 for x values. And of course, since we are at an endpoint here, we know that the derivative does not exist at endpoints of a domain. So we have to exclude -1 and 1 from being, valid values for the derivative. And hence, that's why we get that x is all values in between -1 and 1. All right, so for our next example here, we could take dy over dx, and we can just rewrite it this way, which we can factor out the y in both terms in the numerator. And from here, notice that in our numerator, for our constant solutions, we would have to consider when this is equal to 0, and this would be, of course, when y is equal to 0 and 1. So these would be our constant solutions here. So from that, we'll take what we have here and we'll rewrite everything so that we can solve for y. So, of course, we have dy over dx is equal to this business here. And if we do some rearranging, what I end up having is dy over y times y minus 1. And this will be dx over x. And if we were to integrate both sides, Of course, the right side is pretty easy. This will just be natural log of absolute value of x. On the left side here, notice that we could use partial fraction expansion here. Okay. And that's because substitution rule wouldn't work, but doing partial fraction expansion would make this very easy to do. And so for here, if we do the shortcut for it, then what A would just be 1 over all of this. And since since this term with the A has a denominator of y, we're going to get rid of that. And we're going to evaluate this when y is equal to 0. So that is the shortcut for this particular method to find out what A is. So this is essentially 1 over y minus 1, or y is equal to 0. And this is equal to -1. So A is -1. We'll do similar thing for B. So B, but this time we'll multiply this by y minus 1. And we would evaluate this at y equals 1, because that's the value that makes the denominator go to 0. So this is equal to 1 here. So now that we have that, then of course the left-hand side here, we could rewrite this. Oops, I didn't mean to rewrite that over again. So we take this and we can just rewrite it as -1 over y plus 1 over y minus 1. And we take the antiderivative for both of those. And so for the first one, this would be a minus natural log of absolute value of y. For the second one, of course, we can use the substitution rule. If we did that, let's say let u equal y minus 1, then it means du is equal to dy plus 0, basically. So here we can just do this directly and just say that this is going to be natural log of absolute value of y minus 1. And using our logarithm properties, we can rewrite this as natural log of absolute value of the expression y minus 1 divided by y. So now that we have that, then of course the right side here is just natural log of absolute value of x. And again, I'm purposely leaving off the integration constants here, so that now when I put this all together, this is y minus 1 integral, and this is this. This ends up being natural log of absolute value of y minus 1 over y equals natural log of absolute value of x plus some constant here. Okay. And if I use my logarithm properties here, of course, one other thing that I could do is I could subtract natural log of x from both sides. I'm going to do this here just to save a little room. So if I did that, what I would have is minus here, and that would equal c. And then my logarithm properties would allow me to actually rewrite this way. Now, from this point, of course, we just try to solve for y explicitly, and we can use our logarithm properties again, or in this case, exponential properties, to rewrite this as an exponential equation. And of course, this will be e raised to the natural log of all that stuff on the inside, and it really doesn't matter what's on the inside. We know that e raised to the natural log of whatever is that whatever. So this would end up being this at the end of the day. And on the other side, we'll have e raised to the c. And that is just some constant, okay? Now, because of our absolute value rules, and I'm going to go over here and let's scroll up here for a second. If you remember, whenever we talk about absolute value of something is equal to some expression here, that is the same as saying whatever this is going to be plus or minus whatever this constant is. And of course, from a conceptual standpoint, we're saying, hey, if this is a number and we want to figure out what is the distance of that number is from 0 on the number line, then of course, minus that number and plus that number is going to be that number that's exactly a distance of this much from 0 on the number line. So I'm saying all that to say that here, how we're going to simplify how this equation is going to look is we're going to use that same kind of thinking. So here, using what we just talked about for absolute value, we could say that y minus 1 over xy is going to be equal to plus or minus e raised to the c. And what I'm going to do to make life a little bit more simple for me is I'm just going to call e raised to the c some constant. I'll call it a. Okay. And so from there, all I have to do now is just rearrange this equation to solve for y. So to do that, sorry, I forgot to do something here. Let me rewrite this. All right, so I should have put a plus or minus here. So all of this is going to be a constant, so this should be plus or minus right here, like that. And so in doing that, all of this should be replaced and it'll just replace with an a. Now, part of the reason why we're not necessarily worried about the plus or the minus part in this is because remember that this is, if we didn't have any initial conditions, then it really wouldn't matter. Plus or minus e to the c is still just going to be a constant. In the specific case of us actually having an initial condition, our initial condition is going to let us know, number one, what c is, thus what e to the c is, and whether this is actually going to be positive or whether it's going to be negative. So it's going to take care of all of that. So we don't have to worry about it, okay? Now, with that being said, we just now need to rearrange our equation to solve for y. And so if we multiply both sides by xy, have this situation here. And then I'm going to get all terms with y on the same side. So if I do that, my equation will look like this. I'm going to factor out the y on both terms on the left. And then what this ends up looking like here is y is equal to 1 over 1 minus a times x. And so this would actually end up being our general non-constant solution here, okay? Now, one of the things that I want to call to your attention here, and I've purposely kind of left this alone up until this point, is that if we were to look at, I guess, if we were keeping track of what our X and Y values could be at this particular point, one of the things that we would find out is that our X values would have to be greater than or equal to -1/4, and our Y values would have to be greater than or equal to 1/2. And here's why. Okay, so I'm going to go back up to our original equation here, and notice that we're dealing with the derivative of y with respect to x is equal to what we have here. Okay. Now, if we consider what we're talking about here, if we consider this numerator, and our assumption here is that y is some function of x. So in figuring out what y could be in this situation, we're also going to inherently also figure out what x is. Notice that this is technically a function x in terms of y. Okay, so in other words, if I give you y values, I can figure out what the corresponding x values are. Okay, so if I'm looking at this way, then here, if I draw what this looks like, this is y and this is x, then notice here I could rewrite this way. And so what this is telling me here is I have a y-intercept at 0 and I have a y-intercept at 1. So let's act like here is 1, there is 0. Okay. And notice that I have y squared minus 1. So this looks like a parabola, but it's going to be a parabola going, where normally we have a parabola that looks like this, where this is x-axis, that's y-axis. But because we have x in terms of y, it's going to have to look like this. So that means my parabola, in short, is going to look something like that. Okay. Now, the issue with what I've drawn here is that by definition, y squared minus y is technically not a function if you're looking at it as y in terms of x. Okay, so the way I've drawn this, this is technically not a function. The thing that I want to have consistent is no matter if I look at this as y in terms of x or as x in terms of y, I want this to be a function always. So in other words, I want this relationship here to be 1-to-1, so that no matter if I look at it as y in terms of x or x in terms of y, it always ends up being a function here. Okay. So to do that, I have to restrict what my domain is going to be for this particular function. So to do that, I have to choose what half of this parabola do I want. Do I want the upper half or do I want the lower half? Okay. Now, it turns out that our initial condition actually helps us to be able to figure out which one we're supposed to choose. Okay. Now, recall here that our initial condition for this problem was y of 2 is equal to 1. So mainly saying when x is 2, y is equal to 1. Okay. So that's what it's supposed to be. Now, notice here that what I've drawn a graph of is actually the derivative of this function. So we're not actually going to be able to find this point 2, 1 on this graph. However, this could help us be able to figure out what portion of the parabola we need to choose. Now, if I look here, if I was looking at this parabola, notice that if I was looking at this this way, that this would be the vertex, right? And so here, a way that I could find the vertex really quick is I could let this be my A. So 1 is going to be my A, -1 is going to be my B, and 0 is going to be my C. And of course, we know that for the x-coordinate for the vertex, it'll be minus b over 2a. And in this case, this will be a minus 1 over 2 times 1, which is 1/2. So this lets me know here that vertex here is at positive 1/2. Now, if I did that, if I take this y value of 1/2 and I plug it in to my function here, I'm going to figure out what the corresponding x value would be. Okay. And so if I did that here, have y squared minus y equals x. So if we let y equal a positive 1/2, then we're here, and this is 1/4. And so 1/4 minus 1/2 is a minus 1/4. So we're here. So what this is telling me here indirectly is that I know that my x values need to be, my x values are going to have to be greater than or equal to negative 1/4. My y values are going to have to be greater than or equal to a positive 1/2. Okay. So in saying this, what this is letting me know is I got to choose one of these, and I know that this point has to be in the, this point is going to have to be in quadrant 1. I can't choose this portion because if I do, then whatever point I end up having for my original function, it is going to be in quadrant 4 here. Okay. Even though this is not the same graph, if we actually found out what's going to be the actual antiderivative of this, what we'll end up seeing here is that we still need to pick a value that's going to be in quadrant 1, because this will be some cubic function, and this will end up being some square function here if I actually did the antiderivative of it. Okay, so make a long story short, what I'm trying to say here is that because of this, I need to look at only this half of this parabola to make everything work. Okay. And so it's partially because, well, we know for whatever y, whatever it's going to be, it's going to have to satisfy this condition here. And in addition to that, and I'll tell you another thing. So in addition to that, and this is going to kind of give away what I'm trying to get to, remember that our constant solutions had to be 0 and 1 as well. So all this stuff has to tie in. And in these situations, since we have an initial condition here, and of course this is an initial value problem, we have to have exactly one solution. Okay. So I'm hoping that you kind of see what I'm trying to get at here. If this is our initial condition, and these are my constant solutions, and I have to have exactly one solution, and we just went through all of this business here to show you that, yeah, we would probably have to pick this part for the derivative. What I'm hoping that you see here is that the actual single solution to this particular equation, differential equation, is going to be y is equal to 1. Okay. And so I'm going to finish the problem and show you that that actually ends up being the case. So, but I wanted to make sure that I tied in what we talk about as far as knowing what your x values and what your y values could be in order to make all this work. So let's go back to this particular problem here and finish it out. Okay. So now that we have this situation here, I'll keep this in black. So my initial condition is that y of 2 is equal to 1. So here, if I let that equal 1, and this is a, and I'll let this be 2 here, then I'm just going to solve for a. And so this would end up being 1 minus 2a equals 1. And of course, if I subtracted 1 from both sides here, then of course I have minus 2a is equal to 0. And of course, divide both sides by negative 2, a ends up being 0. So if I look at that, then my y of x function now is that. So we see that our single solution to this particular problem is just a constant function, and that constant function value is 1. All right, so for our last example here, this will be an example to where we will actually use the definite integral to be able to do our whole initial condition stuff so that we can figure out our answer in nice compact form. I also keep along with the tradition of actually doing the traditional way to where we're respecting the dy over dx as y prime of x and kind of going through a long way of doing it for this worked out example here. So, of course, we start this problem the same way. Since it's dy over dx, we want to find out if we have any constant solutions. So we look in our numerator, since that's where our expression in terms of y is. So if we do that here, then one of the things that we can notice right away is that y equals plus or minus 1 would be a constant solution here. Okay. And so we'll keep this in mind as we work through this particular problem. Now, we notice here that dy over dx is the same as y prime. So then we can rewrite this in differential form. So whenever we take our y prime of x here, we could take this and just multiply both sides by dx. And of course, we'll use this differential form here to replace y prime of x dx with just dy. And over here on this side, we'll keep everything the same. From here, we just rearrange this equation to where we have everything in terms of x on one side, everything in terms of y on the other. So if we take this y squared minus 1, divide both sides by it, and then we also take this, multiply both sides by y, have this up here, then of course we'll get y times dy over y squared minus 1, and of course on the left side we'll just have 1 over x dx. Okay. Now, normally what we would do is we would just say, hey, let's just integrate both sides. Here I could use substitution rule to be able to do the antiderivative for this. And of course, the antiderivative for the right side would just be natural log of absolute value of x. Now, if we employ the definite integral technique that I talked about earlier in my video on talking about definite integrals in first order equations, the steps that we need to take here is we're going to let x equal another variable s, and this is just, we're just doing this on purpose to make these two things look different, even though that they're the same. We are also going to let w, which is going to be our substitution that we'll use, we're going to let that be y, which is going to be some function of x. And again, we're doing it just to make everything look different. And here, if that's the case, then we're going, if we take the derivative of x, then we'll just have dx here, ds here, if we take derivative of both sides there. Here, if we were to do the same thing here, the derivative of w with respect to x here, if we wrote all that out, derivative of w with respect to x would just be y prime of x. But of course, if I multiply dx to both sides, then I end up having this, it being in differential form. So we do all this setup here, and then we integrate both sides where we make the limits of integration on our integrals. We let the lower limit be 1, and the higher limit be x. And of course, we're going to do this substitution of letting x equal x equals s here to make everything work. And of course, our y of 1 here is going to be a -2. Okay. So here, if s is 1, then of course we substitute that in since s and x is the same thing. So my point here is that w is equal to y of x, but that's the same as y of s. So I can plug in s to be 1 here, and I know that y of 1 is equal to -2. And of course, here when s is equal to x, plug in x into y of x, it's just y of x. Okay. So when I get all that set up, this is how it ends up looking. So I take this equation that we know of here, and we do the definite integral of both sides from 1 to x, 1 to x. Of course, all this will stay the same here. And on this side, this will stay the way that it's going to be. But to differentiate these variables here with this, we're going to let x equal s just so that it looks different. Okay. And remember here, this is all in terms of s here. But if we want to use the substitution w here whenever we do the substitution rule, so that's why we had this in the first place. In this case, we're going to let, y squared equals 1. That's going to be our w. So that means that we work this all out and make it work. Oh, sorry. No, my bad. No. So here we're going to keep this the way that it is. So we're just going to replace this y here with w, and we'll do the other thing later. So once we have this, of course, the whole point of us doing this is to have this look different so that we won't be thinking that what's going on here and what's going on here when we actually go through the whole operation of everything will be the same. Okay. Although it is, we want it to look different until we're done actually executing the antiderivative portion of this. Okay. So that's why we go through the whole trouble of even doing it in the first place. And it's also the reason why personally I don't like to do it because it's too much to think about to set it up to be able to get it into compact form. All right. So anyway, so we're here, and once we get this set up in the way that we need to have it, then of course I could look at the left side here and notice that I can use the substitution rule here. Okay. And so here's where the substitution part comes into play. So I let u be w squared minus 1. And of course, if I took the derivative of u with respect to w and move some stuff around, I would end up getting this. And so that means that 1/2 of du is equal to w dw. Okay. So that means I could take this situation here and I can rewrite everything in terms of u. So of course, all of this is just going to be 1/2 of du over u. And my limits of integration now, instead of being in terms of s, are now going to be in terms of u. So I'm taking these values here and plugging them into my u function. Okay. Sorry, that's actually in terms of w because it's on this side. So I'll say that again. So over here, everything is in terms of w here. So these values here are in terms of w. So that's why I'm plugging them into my substitution here to make it easy to do. Okay. So I won't have to go and back substitute at the end of the day. So once that's done, then of course, u of y minus x is just y minus x squared minus 1. U of minus 2 is 3. And of course, I factor out the 1/2, and all I have is 1 minus u over du. And of course, from that, I can just take the antiderivative of that real easy. And I see that once I do that, all that works out to be this natural log of absolute value of all this business on the inside here. Okay. Now, so we have that. Of course, this side is easy to do because it's just natural log of absolute value of s, and we evaluate it from 1 to x, and so you see that that's there. And we go ahead and use the net change theorem from Cal A. Write that. We know natural log of 1 is 0, and so that lets us know here that if we're just looking at this, didn't mean to go over that, but if we're just looking at what's left here, notice that we have natural log of something equals natural log of something else. So our logarithm properties tell us that, hey, if you have log of same base of something equal to log of same base of something else, then those two things on the inside have to be equal. And so we end up having this situation here. So now to finish up, we want to now solve for y in terms of x explicitly. So here we just square both sides. And then after that, just rearrange to solve for y of x. And of course, when we do that, what you see here is that we get plus or minus. And so technically, that's not a function, but our initial condition is going to help us choose which half we should pick, okay? And so if we look back at our original problem, our initial condition is going to be y of 1 is equal to -2. So if we were to actually graph this situation here, and I just made this look simple, this is just going to look like some kind of square root function. And in general, the profile looked like this, but since it's plus or minus, got 1 on top, 1 on bottom. Since my initial condition here is y of 1 is equal to -2, that point is down here for this particular parabola, okay? And so, well, it's really not a parabola. It's two square root functions put together with a hole in between here to make a parabola. And so, of course, the x equals 0 part, if we go back here at the beginning of this problem, you kind of see it here that we can't let x equal 0 there. Of course, natural log of x can't equal to 0 there. And so that's another place where it shows up at. If we go back to the very beginning of this problem, notice here that x can't be equal to 0 there. Of course, y can't be equal to 0 either. So because of that, that's why I have this hole right here. And thus, we know from that, if we pick our answer, we know that we're going to have to do the left side of this. So here, we know that we have to choose the negative value for that, okay? And so, of course, our non-constant solution ends up being what we see here. Now, the very last thing I want to say before we end this video is that notice that we also had constant solutions of plus or minus 1 here, okay? Now, since this was an initial value problem, we have to choose one solution to kind of cover everything. And remember the fact that if we had a general solution here, meaning that when we had this plus or minus here, if we did not have the initial condition, we would have a whole bunch of collection of functions that would kind of, well, not functions, but relations that would look like this. But since we had an initial condition, we had to pick a side. And of course, we know that that particular side is the bottom half. And so what that lets us know here is that if we have a constant solution wrapped up into this, It's got to be one of these two, okay? Now, if we look here, notice that, let's see. So there's going to have to be some x value here that we could have to be able to either get a positive one or a negative one. Well, since we have square root of something and we have this minus out here, we know that the only thing that we could possibly consider here is when y is equal to -1, okay? And if you do some playing around here, if you were to actually plug in a 0 here, we would get 0 plus 1, and then of course that would be 1, and square root of 1 would just be 1. So we see that our constant solution here is covered in our non-constant solution here when x is equal to 0. So it's for that reason we can actually say that this is our final answer, and we don't have to worry about stating the constant solution part of this because it's already wrapped up in there. All right, so this concludes the examples on separable equations. I know this was a lot of examples, and I know this was a long video, but I wanted to make sure that I gave you as many different types of examples as possible so that you'll have a good idea of how to attack any kind of separable type of equation that you will see at this point in this course. All right, take care.